All right, College Trig, 8.7, Part 2, last notes of Chapter 8. So some things I noticed as we were working through some stuff. Make sure you notice when you're doing discriminants that you're using straight lines and not brackets. Brackets might imply multiplication or something like that, or matrices, but we're doing discriminants, so it's like the absolute value lines, but just straight up and down vertical lines. Remember the idea of discriminants being the cross products, where you're multiplying like this and subtracting away from there from our discriminants. Remember, for that middle discriminant, that j component, it's a subtraction, where the other two are addition. To find a vector orthogonal to two different vectors, remember, that is just cross products. And other thing I want to make sure we review is, remember that dot products gives you a number, not a vector, and that helps us find angles in between vectors, and it also helps us determine if things are perpendicular or parallel, because parallel vectors will have an angle of 0 degrees between them, and perpendicular vectors will have an angle of 90 degrees. And we have the formula for finding angles between vectors, and it all deals with dot products. So there's some geometric properties that we want to highlight here with cross products. One of the big, most important one is the U cross V is orthogonal both to U and V. The second one we're going to emphasize today is that if we take the magnitude of U cross V, that is the same thing as U, magnitude of U, magnitude of V, times the sine of theta. And theta, again, is the angle between U and V. This is useful because this gives us 1 and 2 options for equivalence here. And the nice thing is that the magnitude of U cross V, the cross product, is the area of the parallelogram. Okay, making sure that U is not 0 and V are not 0. As our sides. So that also means not only that U cross V magnitude is the area of the parallelogram, but also U magnitude times V magnitude times the sine of theta is also the way we can find area of the parallelogram because of this equivalence statement here. So let's go ahead and look at an example here of finding area of a parallelogram. But first, to kind of help you make sense of why that is area of a parallelogram, well, if you consider this vector V here, okay, the length of this is the magnitude of V. We have magnitude of WU here, and we know the length of this is the magnitude of W. And from geometry, we know the area of a parallelogram is its base times its height. And we got to remember the height needs to be perpendicular. So using what we know about vectors, and this being perpendicular to, we have a right triangle. So to get this here would be our perpendicular height. Okay. So we can see that this height is equal to magnitude of W times the sine of theta, because setting up my right triangle, I see the sine of theta is H over the magnitude of W. Solving for H, I end up getting that. So to do base times height, again, that's magnitude of V. That's our base times our height is W times the sine of the angle in between. And again, that's our area. So this is a nice visual representation of why you would get that. Notice for three-dimensional space, you could find the area and volume of a prism here, knowing that we have 6 sides to our prism. So if we had 3 vectors, A, B, and C, you could find the area of that parallelogram on the bottom. Then you could go ahead and find the area of this side of A and B. And notice that this side of your parallelogram would be equal to this side, and as your bottom would be congruent there, and this would be congruent here, and your last ones being the two faces, where you could do C, A, and that would be our front face of our parallel prism, and then that would be congruent to our back face back here. Now it's just getting all over the lap, but you kind of get the idea there for 3 dimensions. All right, so our example here is we want to find the area of a parallelogram with adjacent sides 3 and -2, 1, and -1, 3, -1. So if we get a general sense of what's happening here is starting at our origin, we get some vector that is 3, -2. And let's say we get another vector that's -1, 3, -1, just kind of throwing out those random. We can see that to find this area of this parallelogram, we would have something like this, where we are only given the two sides here, but we can find the area of this parallelogram here. We're going to go ahead and do it with the two equations just to show that both of them will end up being equal out there. So the first one we're going to do is let's go ahead and do the equation on the right to find the area of the parallelogram, where we're going to call this theta here, the angle in between. So first I need to do is find the magnitude of u. So I'm going to have, let's go ahead and call this u and call this v. So u, magnitude of u, is equal to the square root of 9 plus 4 plus 1. And the magnitude of v is equal to square root of 1 plus 9 plus 1, which is equal to the square root of 11, and this is equal to the square root of 14. Then I need to find my sine of theta. So remember, to find my theta, I have the equation of inverse cosine of my dot products over my magnitudes. So my dot product is going to be 3 times -1 is going to be -3. -2 times that is -6. And 1 times -1 is -1 over. Well, I've already found these. I get the square root of 14 over the square root of 11. And this is going to be equal to my theta. Okay, so simplifying this out, I get inverse cosine of -10 over the square root of 154. So pulling up my calculator, inverse cosine of that, and I get my theta is equal to 143.69. And then I can plug that back into this final equation of my area is going to be equal to square root of 14 times the square root of 11 times the sine of theta. So I have the square root of 154 times the sine of my last answer. And I get my area is equal to 7.35, some kind of units squared, because it's area. We don't know what we are talking about with these vectors, if we're in feet, inches, miles, or what have you. So let's go ahead and verify that these equations will give you similar ones. I'll do this in the blue. So I set up my 3x3 determinant here. So I'm going to go ahead and write out the work here. And I encourage you always to show as much work as possible so you can get partial credit if somewhere along the lines you mess that up. Notice I'm making sure I subtract my J determinant here. So I'm setting this up. So if I cover up my rows and columns for I get -2, 1, 3, -1. J, I cover up my middle column and my top row, and I get 3, 1, -1, -1. And for K, the far right column, and again the top right row, and my discriminant is going to be 3, -2, -1, 3. I'm going to go ahead and pause the video here and work through this. Check your answer along. So notice this is my cross product of U cross V is equal to this. So this vector is perpendicular to this. If I take the magnitude of U cross V, I'm going to get square root of -1 squared is 1 plus 4 plus 49, which is equal to the square root of 54, which is equal to square root of 54. And of no surprise, we get the same area, which we should because we're just using a different formula from before. So we get 7.35 as our area of our parallelogram.